The modern spreadsheet long ago outgrew its origins as a two-dimensional calculator. Today, it operates as a highly interconnected logic processor. In professional, financial, and analytical environments, the grid functions simultaneously as a lightweight relational database and a high-speed execution engine. This processing power stems from conditional logic, the ability to automatically alter calculation paths based on incoming data values. By routing data through specific conditions, analysts transform static storage into an active algorithmic process. To build models that survive real-world stress testing, we have to deconstruct the functional architecture of this conditional logic, examining how data is evaluated, routed, and structurally constrained. The foundation of this architecture is the if function, operating as a strict binary gatekeeper for incoming data. Data architects stack these individual gates together to construct recursive, multi-tiered decision trees that can process highly complex business rules. Inaccurate syntax at the cell level creates a chain of logic failures that compromise the entire analytical model. This diagram breaks down the if function's strict three-part syntax: logical test, true payload, and false payload. The calculation engine enforces a rigid evaluation order. The logical test is processed first. The passing data packet must resolve to a pure Boolean, true or false. If the test encounters a non-Boolean error, like an NA lookup failure, the equation breaks. The if function cannot suppress inherent errors. It immediately halts execution and propagates the error code forward, shutting down that specific calculation branch. Assuming a valid Boolean result, the gate directs traffic to either the true or false payloads. Inside the Excel engine, that false argument is technically optional. Professional modeling protocol overrides that leniency. A robust architecture dictates that the false payload must always be explicitly defined, typically as a 0 for numeric fields or an empty string for text. If you omit this definition and the test fails, Excel injects the Boolean value false directly into the cell. In downstream aggregations, a sum function mathematically treats that false as a 0. An average function, however, ignores the Boolean entirely, skewing the denominator. Defining every false state explicitly ensures consistent downstream math and prevents silent data corruption. Real-world business logic rarely hinges on a single binary yes or no outcome. Evaluating layered conditions requires an architectural technique known as nesting. Nesting embeds a secondary if function directly inside the payload arguments of the initial parent if function. Calculating a tiered student grading scale relies on this exact structure. The formula must verify if a score is above 90, then check if it is above 80, then 70, continuing down the remaining tiers. This flowchart maps the nested formula. The calculation engine evaluates the first logical test. If the score is above 90, it outputs an A and permanently terminates the calculation. If false, the engine redirects horizontally, plugging data directly into the next embedded if gate. This creates a cascading logic chain. The engine evaluates each embedded node sequentially, reading strictly from left to right. The moment it encounters the first true condition, the process stops. Subsequent conditions are never evaluated. Through nesting, data architects weave basic binary gates together into deeply recursive, multi-tiered algorithms. Sequential evaluation solves for tiered outcomes, but models often require checking multiple distinct variables at the exact same decision node. Analysts handle this by integrating Boolean algebra directly inside the logical test, specifically using the and or functions. The and function enforces strict inclusivity. Every argument within the and block must evaluate to true. If a transaction meets budget and date requirements but fails authorization, the entire test fails. Conversely, the or function enforces flexibility, opening if any single condition is true. This enables short-circuit evaluation. Because finding one positive match satisfies the or logic, the calculation engine stops checking the remaining arguments in the sequence. In massive, sparse datasets, short-circuit evaluation drastically reduces computational overhead by exiting the check the instant a single condition is met. Historically, Excel restricted recursive nesting to 7 levels, forcing users into complex workarounds. Modern versions expanded that limit, allowing up to 64 embedded logic gates in a single cell. Utilizing this 64-level recursion limit generates overwhelming visual noise in the formula bar. Pushing a spreadsheet to this depth creates an architectural anti-pattern that prioritizes raw complexity over model integrity. It creates a structure known as spaghetti logic. The model becomes systemically fragile. A single syntax error, like a misplaced comma hidden inside the 30th nest, instantly voids the entire calculation chain. At this depth, the software's user interface breaks down. The color-coded parenthesis matching system struggles to distinguish deeper structural layers, rendering the visual feedback useless. Without visual clarity, the code becomes functionally impossible for a secondary analyst to audit, debug, or maintain. A system permitting massive recursive complexity does not require you to build it. Deep nesting transitions a fast logic processor into a permanent, unauditable liability. Building resilient, audit-proof analytical models requires mitigating that structural risk entirely. This demands a distinct shift away from recursive architectures, moving directly toward iterative processing. The modern IFS function provides the exact tool for this transition. Looking at this diagram of execution traces side by side, the difference in structural footprint is clear. The nested architecture drops vertically in a cascading staircase, while the IFS architecture runs in a clean, flat sequence. By utilizing this function, the calculation engine flattens the logic tree into a single layer. The syntax evaluates pairs of conditions and values sequentially. It checks condition 1 and outputs value 1. If false, it slides laterally to condition 2 and value 2. Processing pairs in sequence completely eliminates the need to embed functions inside of functions, instantly clearing the cascading parentheses. Flat iteration removes the structural fragility and heavy syntax risks inherent in deep recursion. The core responsibility of a data architect is securing the integrity of the decision-making pipeline. Mastering conditional logic requires knowing how to build a complex decision tree and recognizing exactly when the architecture demands you flatten it.